Hello and welcome to the dissemination video for Visibility Plugs and Socket. In the video we'll be giving an overview of both WPD's Visibility Plugs and Socket project and Centrica's Cornwall Local Energy Market project before discussing flexibility platforms and market models. Then we'll move on to the two phases of the trial and their findings and give a bit more detail for the findings in relation to baselining. We'll round off with the next steps for the projects before demos of the LEM platform showing the features from both buyer and seller perspectives.
Hi, this is Nicolas Métivier from Centrica. The Cornwall Local Energy Market is a 19 million program funded partly by ERDF, the European Regional Development Fund, and partly by Centrica. Cornwall has been selected for its high renewable generation penetration in the grid, leading to some grid constraints such as congestion or reverse power flow issues at substation level. The program follows two different objectives. The first one is to reduce the carbon footprint in Cornwall through the installation of different types of distributed energy resources, such as network batteries, THP on commercial and industrial sites, or residential batteries on household coupled with solar PVs. The second goal is to demonstrate that the value from distributed flexible resources can be unlocked through the implementation of a local and transparent market mechanism in order to mitigate the risk brought by the renewable generations and to convert it into a network management opportunity for the grid operators, TSO and TSO, in a coordinated way. The program started in 2017 and will finish at the end of the year 2020. Together with Centrica, the project partners are Enside, who deliver the clearing engine within the market platform, National Grid ESO, the TSO, WPD, Western Power Distribution, the GSO, and on the academic side, the Imperial College of London and the University of Exeter.
The Visibility Plugs and Socket project came about through conversations with Centrica as they were drawing up their plans for the Cornwall Local Energy Market project. They were looking for customers to trade on their market platform, and we were looking to investigate the opportunities that third-party flexibility platforms could offer. We knew from previous innovation projects that recruiting customers to provide flexibility services could be very difficult. So we were curious as to whether third-party platforms could offer customers something that we couldn't, and therefore reach a wider range of customers and potentially reduce our recruitment costs. So if you're wondering about the project's rather unusual name, this reflects the early concept for the LEM platform, which acts as a hub performing centralised functions. Each interested party would connect to the socket, this hub, using their own plug, which includes software functionalities specific to their role. For example, it was originally anticipated that the analysis to determine flexibility requirements would sit within the DSO plug, and the aggregator plug would have the ability to optimise services within the aggregator's portfolio. The LEM platform would be the natural conduit to share information and improve visibility of flexibility requirements, flexibility capacity, and the agreements that have been put in place. This is of particular interest to the DSO and ESO, where there's the potential for flexibility services procured by both parties to conflict with each other. For example, if a DSO has contracted services to reduce load on a primary transformer, for example during a winter peak, if the ESO dispatches a load turn-up service at the same primary to meet their needs, this will cancel some or all of the DSO's contracted service.
Hi, this is Sam Weavers from Centrica, and on this slide we just wanted to touch on the point that there are lots of different types of flexibility platforms out there, and that the word flexibility platform can mean different things to different people. So it could mean a network management sort of DERM system that enables flexibility through something like A&M. It could mean a VPP that enables control of multiple different types of assets to provide aggregated services. It could mean a register of flexibility assets and a way for DNOs to see what's registered on the network and contract with them directly and then have the DNOs manage the flexibility contracting process themselves, or it could mean a market itself that runs auctions. So what we're showing here is essentially across a range of different key functionalities, the fact that there are various different products in the market that do different things, and that all of these seem to, or they feed into discussions about what Future World E might be through third-party coordination, but could also be used in Future World B as well, where there's coordination between the DSO and the TSO. So you can see the key functions being ability to see on a map what is registered for sales and buyers, the ability to trade flexibility services with National Grid, or to sell to National Grid, to sell to the DSO, a way for aggregators to sell in, managing of baselining and settlement, and then supplier imbalance and peer-to-peer type services as well. So in this slide, we just wanted to note the two main market models that we have trialed in Cornwall. So the first was what we called quote and tender, which was essentially an electronic version of an existing bilateral tendering process. So the DSO places their request for flexibility at a particular point in the grid at a particular time. Sellers can see that. They can then respond to that particular demand and say what they're willing to provide and at what cost. That data is then given to the DSO. They can walk away with that, do their own contracting processes, work out who they want to procure, and then procure them through the platform and then pay them. The second model that we trialed was more of an auction-based market, where the decision on which seller wins a contract is not made by the DSO through their normal procurement processes, but is made in a market. Namely, buyers' demands and sellers' offers are put into a market platform that we've created. We run a clearing engine that takes the intersection of supply and demand curves to create contracts at the marginal clearing price. So what that does is it enables pricing signals. It's transparent, and it also enables to have purchasing by multiple buyers at the same time. So this is how we can do TD coordination. And it also means that the price that is paid for any given megawatt of flexibility represents better the whole system value, because you have the TSO and the DSO needs as well. Later on in the slides, my colleague Nicola will talk through the various other features that go into the clearing engine, such as considering of asset constraints and consideration of the grid constraints as well, to ensure that the contracts that we make are grid secure. It's also worth noting that in the auctions we separated the reservation and utilisation procurement process, which is in line with European balancing guidelines, and is also what National Grid is moving towards with various of its ancillary services. The key idea here is that the megawatt hour price should best reflect the value to the system at the time that it is used, and that the closer we can push that decision of procurement of the megawatt hour to actual delivery, the more accurate that price will be and the better price signal that will send to the market. Both of the services that were run through the Cornwall LEM were service by service basis, so they weren't a long-term 1 year, 2 year, 3 year framework agreement with the right to call off. They were a contract for delivery of a particular amount of flexibility at a particular point in time, at a particular point in the grid.
As we designed the platform to have both an easy-to-use interface as well as more technical features, we tried to make sure that we had a wide range of participants on the platform. We held an event near the start of the project, which was attended by 10 of the leading aggregators. This was intended to provide an overview of our project and to try to ascertain if there would be any providers who could participate in the Cornwall trial. From the 10 aggregators, there were 2 potential providers who had assets in Cornwall. However, for one party who optimised a number of supermarkets and banks in the area, the effort and time to participate with their customers meant it was not feasible to do so. From the other provider, we had 25 megawatts registered on the platform and participating throughout the duration of the trials. Throughout the project, we've spoken to a large number of businesses in Cornwall for a variety of reasons. This meant we had a long list of 124 potential participants. We narrowed the list down to 24 businesses who would be well suited to provide flexibility services. From these 24, we then had one-to-one sessions with 12 participants where we onboarded them and demonstrated the platform. As you can see from the pie chart, out of the long list of potential participants, only a very small fraction have ended up participating in the trials. There were a number of reasons for this, but one key barrier is the relatively small financial incentive to participate in the fixed duration trials. For commercial operation of the platform, when users understand and can more easily calculate the financial benefit, we would expect higher participation rates.
The Phase 1 trial had some similarities with the way in which services were purchased for Project Entire, another WPD innovation project that looked at flexibility services in the M40 corridor. For this trial, the DSO would publish their requirements specifying what service they wanted, where on the network it was needed, when they needed it, and the capacity for each half hour during the service period. Service providers would then respond with their offers before a set deadline. The DSO was then given a period of time to select the optimal set of services from those available and update the system to notify the providers whether they would be required. There were new features introduced in the CLEM to make the services more adaptable. So where entire services could only be procured by a third party that had signed up to a framework agreement, the CLEM allowed for more casual trading, with a contract only being formed when a specific trade was agreed. While entire services had a fixed capacity throughout, we could specify different requirements for each half hour, tailor requirements to lop a network peak more efficiently. The timescales for trading activity could also be tailored, so that services could be arranged with different notice periods. For this trial, WPD was the only purchaser, so conflicts between purchasers could not be tested. An optimization tool was developed based on Excel's Solver feature. This allowed offer information to be entered, but in reality there were rarely so many offers as to require an optimization tool to make the best selection. The 13 scheduled events for Phase 1 took place between May and August in 2019 and involved 4 bulk supply points and 4 primary substations as locations. The events mimicked the type of services we would procure for seasonal peak management or maintenance window extension, i.e. we would be looking to reduce load on the network so that in the event of a fault, the network would not be overloaded. The trial required a degree of agility in operation. Having set up a schedule of expected events, there were revisions to take account of changes in the set of flexibility providers during the trial period. There were also some events where no offers were submitted, so additional events were added into the schedule to compensate. We found that offer prices were very likely to reflect the £300 per megawatt hour that was advertised on WPD's Flexible Power website as the combined arming and utilisation price for its secure service. It's also the utilisation payment for the dynamic service. It's quite reasonable for sellers to reflect what they think a buyer might be willing to pay. In a more liquid market with price competition, we might expect the prices to be more reflective of the seller's costs, though this would include the opportunity costs of not being available for other services and not simply the cost of, say, operating a generator. In terms of service delivery, we saw a large variation between providers, with values including the extremes of 0 and 100%. We found similar average levels of delivery to that under the trial for Entire, at around approximately 60%, though we need to caveat this as both were small-scale trials with a limited sample size. We expect to get more representative values of average delivery from the Flexible Power platform, which is currently being adapted to make it easier to download and analyse data. As well as the number crunching, there were some other learning points to come out of the Phase 1 trial. Firstly, we found it difficult to provide Centrica with the information they needed to relate customers to the network. This was patched together from separate data sources, none of which was entirely complete. Whilst this was manageable for a small-scale trial, it would not be sufficient to support business as usual. We also found that the network hierarchy we supplied, which was based on normal running arrangements, did not reflect how the network was actually run at the time of the trial. This had the result of changing the point of impact for some services, so that the benefit was received by the wrong transformer. This raises questions about how DNOs can share their future plans. This needs to extend beyond simply listing the expected outages and needs to provide a view of how the network would actually be configured in the future. This is not a function that's currently supported and is actually quite complex. Work will take place within the EFS project, looking at electricity forecasting and flexibility systems to determine the feasibility and practicality of this. Finally, the additional adaptability that was built into the platform did not turn out to be that useful in practice. The simplicity of having standardised timings was found to be far more beneficial. Again, in a mature market, then a fixed week-ahead purchasing schedule would be complemented by day-ahead and intraday trading. In the Phase 2 trial, the services were purchased using a spot market, with both DSO and ESO purchasing from the same market. The trial incorporated periods where the DSO was the only purchaser, where the ESO was the only purchaser, and when both parties procured services concurrently. The optimization in this case was not by the buyer assessing their particular set of offers, but took place within the market platform, which found the optimal trades for all purchasers and all buyers together. The algorithm that matched bids and offers also incorporated novel features designed to manage conflicts between buyers, such as ensuring that trades did not result in a power flow that would exceed network capacity. Enside, who developed this algorithm, have kindly agreed to cover this in more detail later in the presentation. Another difference in the purchasing process was that there were separate stages. There was one auction to reserve service capacity, which could be held up to 3 months in advance. There was normally on a week-ahead basis. Those customers that were successful during the reserve auction then took part in the utilization auction the day before service delivery. The customers involved in the Phase 2 trial were largely the same as for Phase 1, except that the flow battery that took part in Phase 1 was unable to continue. However, it was replaced by an ice manufacturer who could adjust their refrigeration load.
The honeycomb on this slide shows an overview of the main features and capabilities of the platform. One of the key concepts we want to promote through the platform is really how the local trading of flexibilities can be achieved in a transparent way, highlighting that such a transaction can be robust, grid secured, and maximizing the profit for the market participant in a fair way. It starts at the core of it with a clearing engine provided by Ensign and running automatically in each auction that maximize the social welfare to select the optimal set of flexible offers based on the TSO and DSO request or bids. We have been following a pay-as-clear approach, and out of the clearing results, we can reveal price signals at grid node level and based on the grid constraints. Hence, it gives incentives for the market participant to expose their flexibilities at the right location. We have also decided for the trial to split reserve and utilization auction. Reserve auction allows the buyer or the grid operator to guarantee the availability of flexible power volume for a given time interval and grid location, whereas the utilization auction allows to specify the volume of energy expected then to be dispatched again for a given time interval and grid location. In the context of the trial, power capacity of flexible resources have been procured on long-term basis through the configuration of reserve auction, 3 months ahead, or week ahead, and the energy delivery requirements have been procured in a more accurately fashion through day-ahead or intraday auction when actually the renewable and load forecast enable a better identification of the constraints. Obviously, bids or offers are price sensitive to clear the market, and they take into account, as well as contract, the technical constraint of the assets through the definition of a generic market product that has been based on existing ENSOE standard and implementation guide that are used at the wholesale level for reserve resource process management. As mentioned earlier, T&D coordination is also a key aspect we want to test to manage the T&D conflict. Those conflicts are managed in a two-step approach. First, the platform portal exposes dashboard views, allowing the grid operators to be aware of the T&D request and to manage the conflict manually before the auction runs. Then, we have predefined rules that have been configured within the clearing engine to remove the conflict in an automated way. As an example for Cornwall, DSO has been taking the precedence for requests conflicting as part of the same auction, but with some exceptions, such as when TSO has contracted his capacity beforehand. In this case, he keeps his capacity available as previously reserved. Last but not least, contracts created are grid secured by ensuring as part of the clearing optimization that the flexibility selected does not violate any headroom at substation level. Headroom corresponding actually to the substation power margin available to support flexibility transactions. From the point of view of the market operation, the platform covers the full end-to-end journey. It means all the different processes required to run a market end-to-end are currently supported. So from the start, although there has not been any formal pre-qualification process with the sellers, the platform exposes a step-by-step web user interface or API, allowing participants to register their site and asset, aggregated or not, with their technical characteristics, such as minimum or maximum activation time, ramp rates, and so on. Then we import a simplified hierarchical view of the grid model through a standard interface that can be SIM compliant, and it contains a definition of the constraints expressed in the Cornwall context as headrooms for flexibility exchanges at grid node level, either upward or downward and based on the power limits of the substations. We offer then the capability to receive and validate functionally the orders from market participants through, again, a user interface or REST API. We schedule and orchestrate the auction executions for different time frames. Again, for the purpose of the trial, we went from 3 months ahead up to intraday market processes. And once created from the clearing results, we manage the contracts and notify the involved market participants. It is also worth noting that the platform is actually not responsible for sending dispatch or control signals down to the assets. We indeed just publish contract notification award towards participants in order to make them aware that their resources have been selected for reserve or utilization at a given location and for a specific time interval. Then, once the dispatch event is over and after having received and imported the metering data, we assess the performance of the dispatch by computing the baselining, by leveraging a demand response method based on a similar day approach and used in the standard market design in US, and we run a settlement process to compute the final costs and distribute the payment and invoicing over the different sellers contributing to a contract.
Hi everyone, I'm Keno Merckx from Inside, and I will briefly discuss the market clearing mechanism. So obviously the starting point is the user interface for the platform developed by Centrica. The different users can enter their bids, and we can create the book order, which is the list of all the bids on the market. Then, the book order is given to the clearing engine developed by Inside. The main goal of the clearing engine is to use highly advanced analytical tools to output a price for the electricity, but also a cleared volume, which is a list of accepted and partially accepted orders. You see on the right a supply and demand graph. We'll use those to define an objective function for the clearing engine to decide which orders are accepted or not. Before deep diving into the clearing mechanism, a quick recap about supply and demand graphs, which is a basic concept used in macroeconomics. First, let's talk about the demand curve, which is a decreasing function that indicate the relationship between the price of a certain product in the market and the quantity that the buyers are willing to acquire. You see on the right an example of a demand curve for a certain product on the market. You see that when the price is very high, fewer people want to buy your product and the quantity is very low. But obviously, if the price decreases, more and more people want to buy the product on the market and the quantity increases. We can now talk about the supply curve, which is an increasing function, and describe the relationship between the market price of a product and the quantity that the suppliers are willing to sell on the market. Again, on the right, you see an example of a supply curve for a certain product. If the price of a product is very low, only a small group of suppliers will sell the product because the margins are probably small or negative. Now that we have a basic understanding of supply and demand graph, we can talk about social welfare, also known as market surplus. From a geometrical point of view, the social welfare is the area between the demand curve and the supply curve. You see on the example on the right that the welfare for the people at the top of the demand curve is defined by the gap between the price they are willing to pay and the market price. For a supplier, the welfare is the difference between the market price and the minimum acceptable price. So very roughly, the goal of the clearing engine is to select a cleared price to optimize the social welfare. Obviously, in our case, the social welfare is an analytical function and we cannot just draw demand and supply graph and compute a geometrical area. So the next question is, how can we solve the problem then? To answer that question, we need to talk about mathematical optimization. In mathematics, optimization problems are defined by two things: an objective function that we are looking to optimize, and a set of constraints. If your constraints are nice enough, they will define a convex area in a highly dimensional space. To solve the optimization problem, we need to evaluate the objective function in every single point of this convex area. Obviously, the whole process takes a lot of time. But using advanced algorithmical results, we can speed up this process significantly. At the end of the geometrical search, we obtain a point that will maximize the social welfare function. So regarding the optimization problem that we are interested in for the clearing mechanism, we already talked about the social welfare maximization, and now we can talk about the several constraints we need to deal with. In our optimization problem, we can define three groups of constraints: grid constraint, order constraint, and economical constraint. The larger set of constraints is the order one. Those constraints ensure that the model takes into account the different kind of assets we are dealing with. For instance, if someone uses a battery to supply electricity into the market, into our model, we need to take into account the fact that the battery has a maximum capacity, and also you cannot activate the battery 24 hours a day. The battery has a recovery period every few hours. The second set of constraints is the grid constraints that are related to the network itself. For instance, we use maximum line capacities to ensure that the energy flow through the network is not too high for obvious security reasons. And last but not least, we have the economical constraints, which ensure that nobody in the market loses money. For instance, because the model tries to optimize social welfare, the algorithm could accept an offer below their minimum price for the greater good. Obviously, we want to avoid that, so we set a lot of constraints to ensure that no accepted orders are out of the money. In the same idea, we have similar constraints for the rejected orders. Finally, let's talk a little bit about conflict management between the DSO and the TSO. Because we work on several time frames, we use the first come first serve rule. For instance, if you buy flexibility 1 month in advance, the network capacity will be updated for the 1 week in advance auction. Now the tricky case is when the DSO and the TSO want flexibility in different directions inside the same time frame. In that case, the DSO has priority on the TSO. So that's it for the clearing engine and the conflict management. Thank you.
So, reflecting the two-stage auction process, we have two sets of prices. Reservation prices averaged at around £18 per megawatt per hour, which is considerably lower than the default value for Flexible Power's restore service of £125. However, that value is considerably higher than the typical reservation prices for store, which are typically in the £3 to £4 range, but this reflects the greater volumes secured under store contract that cover a month at a time. Utilisation prices, however, averaged around £280 per megawatt hour, bringing the combined total in line with the Phase 1 mode price of £300 per megawatt hour. Prices were less concentrated around the average value than had been the case in Phase 1. In terms of service delivery, there was an even wider spread of calculated values, going from delivering twice the required response to negative values, which indicate that the response was in the opposite direction to that required. So, for example, a demand had increased where a demand reduction service was expected. The prevalence of low delivery values reflects the trial plan, including many events that would be served by domestic battery clusters. Having noticed unusual delivery values in Phase 1, this was an area that needed more investigation. So this resulting frequency distribution is not reflective of the whole set of flexibility providers, but skewed by having a greater prevalence of the domestic battery cluster events. Phase 2 also introduced a more sophisticated method for baselining. We found that initially delivery was being underreported because of an adjustment designed to ensure that the average baseline was corrected for conditions on the day of delivery. This was accidentally capturing the impact of customers ramping up ahead of delivery. This artificially raised the baseline, resulting in lower levels of delivery being reported. This adjustment was corrected so that it excluded the half hour immediately before delivery, and after this correction, the results were broadly in line with expectations. One of the other differences between the LEM and WPD's flexible power platform is the metering that flex providers are required to have. For flexible power, metering captures the provider's load or generation at 1 minute resolution. For CLEM, half metering is used. Given the smart meter rollout, half-hourly metering will be an easy standard for customers to meet. One concern in using half-hourly metering was that it would offer flex providers an unfair advantage, with providers compensating for periods of under-delivery with periods of over-delivery, which does not produce the DSO with the same benefit as a steadily delivered service. The chart on the left shows an event where the green line represents the power delivered as measured at minute resolution. Early in the event, the delivery falls below the yellow line, representing the 95% threshold where penalty payments begin. And for a short period, the delivery even falls below the red line, which represents the 63% threshold where payment stops completely. As there are no rewards for over-delivery, the payment for this event will be reduced to reflect that dip. However, the blue line shows what a half-hourly meter would have recorded for that same event. For the first half hour, the average is exactly in line with the yellow line, the 95% threshold, so no penalty is applied. As the second half hour also has a good rate of delivery, the full payment would be made. This example shows how half-hourly metering could potentially skew results. However, a fuller analysis of a wider range of events using the data from the entire trial suggested that while there was the potential for benefit, there was also the potential for averaging effects to reduce the calculated delivery. The chart on the right shows the frequency of events where a benefit was seen. As you can see, in the vast majority of cases, the difference is insignificant. With the exception of a couple of outliers, the cases where there is a small advantage or disadvantage tend to be balanced, such that there is no systematic benefit in one type of metering over the other. We also compared the days and times used to form the baseline for the Entire and Clem projects. For Entire, the working days for the first 3 full weeks of the previous month were used, and the baseline reflected the average load between 3 p.m. and 8 p.m. This had the advantage that it could be calculated in advance and converted to a target load value for the flex provider to achieve. For Clem, the previous 10 working days were selected, and the baseline was the average value for the half hours over which the service was delivered. Thus, a service delivered at 1 p.m. would use the baseline value for 1 p.m. On the chart, you could see 4 straight lines representing the baselines calculated for 4 events using the Entire methodology, and 4 wiggly lines representing the baselines calculated for the same 4 events using the Clem methodology. For some events, there's a big gap between the 2 baselines, especially for events near the end of the month. So the difference in methodology would drive very different results and different payments. It appears that the Clem baselines could benefit from some smoothing being applied, but it would also be possible to communicate the baseline to flex providers before the event to allow them to operate the equipment to achieve a particular value of load and generation in the same way as was done for Project Entire. Some assumptions or risk margins would need to be applied to account for the day of the event adjustment, which can't be provided in advance. This is a further area for investigation, and we're particularly interested in working with the Open Networks project, which has got a product relating to baselining in particular.
As part of the wider Cornwall Local Energy Market project, we installed battery and PV systems at 100 homes throughout Cornwall. We then aggregated the batteries together to respond to some of the platform trial events. After the events, we used 30-minute smart meter data to compute our baseline and assessment processes. For the Phase 1 events, we had smaller battery pools of between 6 to 8 batteries per event and found that for a couple of events there were some discrepancies between the performance calculated using the smart meter data and the 1-second battery system data. For one event, we found that the performance calculated varied by up to 50%. For the Phase 2 events, we had larger pools of around 20 batteries per event and found that the performance calculated using the smart meter data correlated to within a couple of percent for every event when compared to the battery system data. This suggests that our baseline methodology would be suitable for residential flex when the households are sufficiently aggregated together, but for smaller events, i.e. at an individual street level, our methodology would not be suitable due to the variability of individual household loads. However, more research would be required to assess the number of batteries and overall capacity required to overcome this issue, as well as if any other baseline methodologies might be more appropriate for small pools of residential assets.
In terms of next steps, WPD is continuing to investigate flexibility services within innovation projects. EFS will be purchasing and using flexibility services in operational timescales and will use multiple platforms. Intraflex is exploring options to manage the imbalanced position created for suppliers by the DSO's use of flexibility services. And FutureFlex will be looking at how we can get the most out of domestic customer flexibility. We're also continuing the rollout of flexibility services as business as usual. We've recently developed a flexibility map where our future requirements are shown, as well as some high-level signposted for expected services further in the future. We're adopting a flexibility-first approach, where all major load-related investments are assessed for non-network solutions, with traditional reinforcement no longer being an automatic first choice. The baselining approach for flexible power is currently undergoing a review, and we're looking to use the Cornwall local energy market to provide real services in the Hale area. So just to flesh out our flexibility first approach in a bit more detail. This starts with the forecasting of system needs and publishing both longer term signposting and the shorter term requirements. We want to make markets accessible, so we're looking to provide multiple routes to market, and the CLEM fits in very well here. One of the reasons for non-participation in the trial was the lack of rewards, and we understand that flex providers need to make a case for investment. The service requirements shown on the flexibility map often cover multiple months and several successive years. We're also looking to operate in a transparent way where the process can be trusted. When it comes to dispatch, we want the market to grow, so we've included principles to prevent services being concentrated to a few providers, while still reflecting the DSO requirements for value, security and operability. The pricing strategy used for flexibility services will reflect the market maturity of each energy service area. Where there is little liquidity, then fixed prices will be used. As liquidity increases, then the pricing will reflect pay-as-clear results before moving on to full market pricing.
So to conclude for Centrica, the key points are that we are live and flexibility transactions are ongoing as we speak, and it will be still the case as a minimum till the end of the program, in the end of 2020. We have really developed the platform in a way that it can be scaled horizontally very easily to cover a wider area or go deeper in the distribution grid at lowest voltage level. We can also spin up a new instance quickly by importing a new grid area. So it is key for Centrica to disseminate the concepts related to the auction-based T&D coordinated flexible market. We are now looking for new geographical areas in order to deploy the technology and add more use cases as part of the platform. On that regards, other pilot projects have been secured, notably in Belgium, where the LEM concept will also be tested live. Thank you.
So this is essentially just a quick video walkthrough of what the buyer sees on the platform, so they can see the bids and contracts that they have made or won, both by time and by location. They can then also see what the other network operator is doing on the platform. So this is the core of the TD coordination function. So they can see that National Grid has created a bid that might conflict with what they're doing. Where it says Centrica obviously says WPD in the live version. They can then also see if they want to win a contract on a particular date in the future, what auctions are upcoming and when they need to have their bids in by. They can then also see nodal pricing essentially, so they can see the price of flexibility services both for reserve and utilization at different points in the grid. They can then go in and create two different types of bids, reserve and utilization or delivery. They can choose a point in the grid or a substation where they want to do that. They set the time for doing so. They can then also set the megawatts that they require on that particular day, whether it's up or down, whether they need the full amount that they've asked for or whether they want anything above a certain amount. Put in their pricing, and then they can then also repeat that bid as well, and that means obviously they don't need to go in and create a bid for every single hour that they want. They can just say, I want this every Tuesday to, well, here we go, every weekday, and I want this to happen for the next 3 weeks, and that will then create the bids that they need, and they can then publish those, because as we said, the contracts are for specific points in time. They're not framework contracts, because that gives sellers better clarity about what else they can do with their assets. Once they've won contracts, they can then go in and see for their reserve contracts what they've won per half hour. They can then adjust the utilization volume that they want. They can either set that across the whole of their bids, or they can adjust it on a half hourly basis. It then also tells them when they had to get that utilization information in respect of the relevant utilization auction. They can see essentially the history of all the contracts that they've won. So this is a walkthrough on the seller side of the platform. So this shows on a map where my sites are and where in the grid they're connected. So you can see this site goes into Tor Point, and then I can also see obviously the offers and the contracts that I've won or have created. As a seller, I can see what the buyers are trying to procure. So I can see that by date or by location. So I can click on a particular part of the grid and see when I might be able to provide some flexibility to the buyers. I can then see when I need to create my offers by in respect of a particular delivery date, and then I can see the prices for flexibility at those different points in the grid. I can then obviously before that, if I want to sell something, I need to register a site, which we can do here through the UI. And this is done easily on the website, but we could also have an API that allows, for instance, an aggregator to bulk upload a whole range of sites in one go. I register the site capacity, various contact details here as well. And then once I've done this, and registered my site, I can go through and I can register an asset for that site. So if I want to add an asset, I can say it's going to be demand response. For instance, I can then say what else I use the asset for. That's just a sort of a research purpose thing for now in Cornwall. I say key details of the asset, and then these optional parameters are essentially parameters that the clearing engine will take into account if I want it to. So if I don't put any of these things in, then the clearing engine will just assume that you can deliver whatever offers you've put into the system. But if you put in these ramp rates or response times, then we'll ensure that all the contracts we create are physically feasible for you to deliver. I can then go through and create a reserve or a utilization offer, and I can do that either by site or as an aggregated unit. So as an aggregated unit, instead of selecting this particular demo site, I would select a grid node, at which place, I suppose, I would offer to create a certain positive or negative megawatt deviation on the system. And so that gives flexibility for people. So the other point here is that I can create offers either through the UI, or I can do it through an API as well. So if I am an aggregator and I've got a system and I just want to expose a bulk upload of offers, I can do so, and I don't need to go through onto the UI every time I want to create an offer. Once I've created my offers, I can review them, I can manage them, I can edit them, I can delete them, and I can review them on the system.